Okay, so here's going to be a little video on an introduction to groups. I suggested watching some other videos by the visual group theory guy and also by Michael Penn. I think those videos are very good, and they're especially the visual group theory is sort of very motivational. Although um, part of what he's doing is trying to get a finer point on groups across. So some of what he does is maybe actually a little harder to understand because he's trying to do it visually. But anyway, I mean, for that sort of motivational stuff, I'm going to say see those videos. They're done really well by people who, are professional video makers, more or less. I'm going to jump right in and just sort of give a definition of groups and look at some examples and prove some basic facts. Maybe not quite in that order. So a group is a structure, an algebraic structure. So I will kind of use the letter G for two things here. So it's maybe I won't use these sort of square brackets. I'll use these. So G, this will be a set. Then there'll be an operation. Usually this operation is plus or times or composition or something like this. So star will be a binary operation on G. So what does that mean? It means that star is a function from G cross G to G. Okay. And E, this will be an element of G. Okay, so very general. We just have a set of objects, binary operation on that set, and a particular element in that set, and they need to satisfy some axioms. Not very many. So, so one is associativity. So what this says is it says for all A, B, and C and G, A star, maybe I'll use this star instead. It's easier for me. B star C is equal to A star B star C. And because of this, we don't have to worry about parentheses at all, right? So we can just write things. In fact, we will write things very often like ABC, right? And this could mean, it could mean AB and then C, or it could mean A and then BC, and it doesn't matter. That's what this tells us, right? So 2. E is an identity for this operation. So star identity. This axiom is different because it says something exists, namely this E, right? And so it says that again, for all A and G, A star E equals E star A equals A. You need both of these. You could have a setting where A star E is equal to A, but E star A is not equal to A. So you could have a right identity or a left identity that's not both. Here we want a two-sided identity. And then 3, we're going to have star inverses. And so this one's also a little bit different. It says for all A and G, there exists a B and G, such that A star B, I'll put the star in there for now, equals B star A equals E. Okay, so once you have an identity, you can have an inverse. So every element of a group has an star inverse, meaning this thing here holds. Okay. Okay, so let's see. So, one thing to note, commutativity. Which is A star B equals B star A, is not assumed. Okay. If this holds, if commutativity holds, then the group is called commutative, or it's called abelian. So G is an abelian, or commutative group. Let's see. Spelling is not my strong point. If and only if for all A and B and G, A star B equals B star A. So commutativity holds. So you're used to doing things where you have commutativity and associativity. When you have those together, it doesn't matter not only what order you put them in. I mean, sorry, it doesn't even matter how you group them, but also what order you put them in, right? So if you have commutativity and associativity, then A, B, C, D would be the same as A, C, or C, D, A, B, would equal. So they're all the same, right? It wouldn't matter what order you do it in. It's kind of like, you go shopping, you throw stuff into your basket, some things in there, and when you go to pay for them, if you don't have commutativity, then the order in which you put them in or pull them out matters, like how much you have to pay, right? So that would be strange, right? So when you're just adding up prices, normal addition is commutative and associative, so it doesn't matter. So you can pull them out in any order and add them together and you're good, right? It would be strange to have a shopping cart where it mattered what order you pulled them out in terms of, as to how much the price was. But that can happen if you're non-commutative, right? So you actually use associativity and commutativity together a lot. So here you have to be careful. So in general, groups are associative but not commutative. And a good example that you should know pretty well would be like matrix multiplication or function composition. No, you have to have inverses, so you have to restrict things a little bit. Before doing examples, I want to just do two like simple proofs. So one is that the identity is unique. Okay. So I guess, we have a thing labeled E. Maybe I shouldn't have done that. Maybe I should have just said for the identity one to make this a little bit more clear. Instead of actually putting E into the structure, I'll just write it down here. Here, let me step out of this for a second. I could have written for star identity. I guess you have to be a little bit careful to do this correctly. So I could have said just there exists an A and G such that for all B and G, A star B equals B star A equals B, right? So I haven't sort of fixed either, right? So suppose I had done that. So I had associativity and I have this. And that's all. So I have the first axiom associativity and I have this. Then we would have the following. We would have that. So this could be like a little easy theorem. Any A satisfying this is unique, right? So there's just one A, just one A and G satisfying. I'll call this thing here star. I'm using star for multiplication. So I'll call it dagger. Okay. Dagger is what we call this symbol. It looks more like a dagger in tech, right? I guess it looks kind of like a cross here. Being GC, I could call it cross, but I don't know. Maybe that's bad, so I'll call it dagger anyway. So let's see why that's true. So suppose that I had two things, A and A prime satisfy star. Sorry, I'm saying star satisfy dagger, right? Then, well, what do I know? Well, A prime would be one of the B's that work for A, and A would be one of the B's that work for A prime. So I would know in particular that A star A prime is equal to, thinking of A as, thinking of A satisfying dagger would be equal to A prime, right? On the other hand, A star A, thinking of A prime as being the thing satisfying dagger, right? This would be equal to A, right? So A prime is the identity, so A times A prime is A. Here I'm assuming A is the identity, so A times A prime is A prime, but then we have A equals A prime, right? So this would imply A equals A prime. So there's really just one, right? So we're done, right? So really simple proof. So if there's an identity, there's only one, and that's why we can just call it E, right? We can say there's that thing, which is the identity. So once we have 1 and 2, right? So we have associativity and identity. Let's say we have, and we have, say, B and G, right? So we also have 3, and 3. So that's the one that says we have inverses. So we have B and G. Suppose there were 2 inverses, right? Suppose A and A prime satisfy satisfy A. I'm not sure why it's doing that. Sorry. A times B equals B times A equals E. Remember, identity is unique, so I can just say that. And also A prime times B equals B prime times A equals E, right? So then what I would get is this. I would have A prime, oops, I don't know why I wrote a star. I would have A prime equals, right, A prime, I keep writing star instead of prime, A prime times E, which is equal to A prime times B times A because of this, right? Oh, and I'm dropping the star, sorry. So since we have the associativity, it doesn't sort of matter where I put parentheses, so I can kind of, anyway, I'm going to just drop the star. So, and this is equal by associativity, A prime B times A, right? And then A prime B, because of this, is equal to E. So this is E times A, and that's just A, right? So I have A prime equals A. So in particular, we've proved theorem. Why does it keep doing that? For all A and G, there is a, I'm not sure why it does this to me right now. There is a unique B, unique one and only one B, such that A, B equals B, A equals E, right? And because of this, we can define A inverse equals that unique B. Oh, I have no idea. I've never had it do that to me before. Okay. And it's really important maybe to use this A inverse instead of like, I mean, here we're sort of using a multiplicative notation. It's really better not to write 1 over A. Writing A inverse is better because we don't have associative, I mean, we don't have commutativity, right? So B over A really doesn't make sense because you need to know the order. I mean, B A inverse might be totally different than A inverse B, right? And if we were writing this like over thing, then this would be written B over A, right? And this might be also written B over A, and we don't know which one it is, right? So you really don't want to use this kind of notation. When the operation is plus, right, so that the inverse is minus A, right, then when we write plus as the operation, it's always going to be commutative. So in that case, it makes sense to just use the minus A. Again, it's a little subtle because we use many different operations, right? So some of them act like plus, some of them act like times. We usually think of times as being being commutative, but not always, because again, if you have matrices, matrix multiplication is not commutative. And anyway, you have to just be careful now. Good. All right, let's actually use that for a nice little argument. So I'll use this uniqueness fact. Right. Let's show that Oh my gosh. I really don't know what I did. I have to fix this. Actually, I'm gonna pause for a second and see if I can make it stop. Okay, hopefully it will stop doing that thing that it was doing. Okay, now let's try to use this. So let's show that AB inverse is equal to B inverse A inverse, right? And so because of this uniqueness, I see this didn't even, when I had to quit this and restart it. So this was saying for all A in G, there's a unique B in G such that AB equals BA equals E, right? That's what should have been there. Good, all right, so let's prove this. So all I need to do is I need to show that AB, in order to show this, I just need to show that composition, right, that product right there, gives me E, right? But if I write that, then I can use associativity to get this. And this, of course, is A, E, A inverse, right? And then I can, to be formal, I can use associativity again, right? So this was A inverse, right? Using also the fact that E times A inverse is just A inverse, and this, of course, is just E, right? So this times that is E, right? Now, actually, we need to check it on both sides. So we do exactly the same argument. B inverse A inverse as a thing, right, times AB, right? And you do the same argument. You combine those, you get E, and then you get E, so this is also E, right? So what we see is that this thing in the box right here times that box right there is E, and similarly that box right there times that box right there is also E, and so that means that this, thing that we constructed is in fact AB inverse. Well, why is that true? Well, there's only one thing, because of the uniqueness, that satisfies those two equations, namely the inverse of AB, right? So we know that. And this is important. We use this all the time. So if you take the inverse of a product, you swap the order around, right? If we have commutativity, it doesn't matter, right? So, just keep that in mind, right? Good. So there's some nice sort of little, theorems. It's kind of three theorems, right? So the identity is unique, inverses are unique, and the inverse of a product is the product of the inverses in the opposite order, right? So there are three little theorems about groups. Okay. Now, in terms of examples of groups, there's a bunch. So obvious examples of groups are Z with plus and zero, right? Q with plus and zero, R, all sorts of number systems, right? With plus and zero, complex with plus and zero. Okay, lots of these things, right? So these are all abelian groups. They're all commutative, right? Oh, and by the way, an important one that we just studied a minute ago is Zn, right? With plus n, and it's zero, right? Maybe we call this 0n or 0 bar or something, right? But we have that. Okay, these are all additive groups. If we look at the multiplicative side, 0 doesn't have an inverse, so we can't have 0, but R star, typically if we have a thing with a 0 and we want to throw away the 0, we just put a star there. Now here we're going to look at the multiplicative group here. So R star, so R star, which will be just R star, and then times and 1, right? So now the identity is 1, right? Q star, right? Equals, again, I'm sort of overloading these two symbols here, times and 1, etc., right? Now you have to be careful. Z star is not a group because you can't, 1 over 2, for example, right? 2 has no inverse. All right. So, you have to be careful. This is our first example where you take a number system and you don't have a group we definitely have a product on Z, but it's not a group. Okay. The ZNs are even more interesting, but let's save that for just a second. So as another example, we might have N by M matrices over some, field in general, C or F or C or R or something else. It's a Q, right? I'll just say R here. All right. So under addition, right, with the 0 matrix, right, that would be a group. M n by n r star. Whoops. Oh gosh, now this is doing a silly thing again. Oh no. Oh, okay, let me just pause. Okay, I had to stop again because of problems with my thing. Let's see if it starts working. It makes it just that much harder to do things. So let's say I have n by m matrices. That's doing that again. Great. Over r star, so not 0, right? Then times, and then the 1 here will be just the matrix, which dang it. Okay. Okay, I'm having all sorts of problems with this thing today. So this will be the matrix of all ones, right? M by n matrix of just ones, right? And oops, I don't know what this is doing. It's going nuts on me. So here the sorry, this isn't the normal product. I don't know. Maybe I'll call it like dot star, right? So let's say I'm in 2 by 2, right? So what I mean here is something like this, dot times, right? This is kind of notation from MATLAB. And let's say 3, 2, 1, 4, right? So I'm just going to element-wise, entry-wise multiply. So 2 times 3, 2 times 3, 1 times 1, 4 times 4, right? Like that. So it's not normal matrix multiplication, it's just corresponding elements multiplied together. So this kind of thing, clearly, associativity holds because we just need associativity of multiplication. If I multiply with an all one matrix, I just get that matrix back. It's commutative, right? That should be clear. And the matrix of all ones, sorry, let's say I've already done that. Oh yeah, and the inverse will just, since these have no zeros in it, the inverse of one of these things will just be where I invert each element, right? So that's a group. It's a commutative group. Okay. More interesting is GL in R. So these are A, which are n by n matrices over the reals. And again, this can be over any field. It could be Q, could be C, could be something else. With the property that A inverse exists. Okay, and that's equivalent to saying the determinant of A is not 0. Okay, so generally this is a really important and somewhat complicated group, but it's a group, right? So it's a group under normal matrix multiplication. So okay, a more interesting group than the ones we've looked at so far is Zn, which we have studied already. But if I have plus and 0, this is plus sub n, right? So it's acting on integers modulo n. So this is a group, and it's a abelian group. And we saw that UN, which is the set of all A and Zn, such that A inverse exists. Remember, we have a notion of multiplication in here. This is a group, so UN equals the group, the set UN. So again, I'm sort of using this in two different ways: the group, the set. Okay, and this will be under multiplication and 1, right? In really important case is when n is p in prime. Sorry, I say n is p. When n is prime, will mean that un is actually everything except 0. So in that case, it's Zn star, right? So we're just throwing around 0, and then Zn star itself is actually a group. So this is really, really important. So like Z, for example, Z5, right? Z7, right? These things like this. Every non-zero element has an inverse. Every non-zero element has an inverse, right? And we know how to find these inverses using Bezo's theorem, right? So don't forget that. That's one of the things we'll use Bezo's theorem for, because it's not always so easy. I mean, in Z, I don't know, what's a big prime? Is 1001 prime? No, some big prime, right? What's the inverse of 225, right? These things are maybe hard to find, but with Bezo's theorem, it's not so hard to find. Let's see. One thing to note is that Cn here, if I have a, this is typically, I mean, this is basically the same as Zn, except usually when we have the cyclic group, we think of it as being multiplicative, right? So we have something, a group, I mean, one obvious example is where we have these like rotations of a polygon, right? So where this would be rotations of a polygon or something like that. You know, so this would be some r, right? And so rotating by nothing, right, would be e. And you have a single rotation. This has what, 6 sides, right? So then we have our R1 would just be a single rotation, R2, right, etc. up through R5. Then we do R again, we're back to the original place, right? So that's E again, right? So then we're in a situation, by the way, the way we would denote this group is generated by R, right? And so that would be, you know, R0, R1, just the powers of R, R2, you know, to R like 5 in this case, right? Now this group is a multiplicative group, right? But it's isomorphic to Z5, right? And the point is you're sort of adding the exponents. If you think about the exponential addition corresponds to the multiplication, right? So R, you know, K, R, N, Rm here, say I'm working in Cn, right? It's generated by a single element R, right? Well, this would be R to the K plus M, right? But it's really K plus M, you know, because it only goes up to N, right? It's really K plus N mod N, right? And so the algebra, you're multiplying, right? But the algebra turns out to be just the same as the algebra in Zn, right? So these are two different ways of writing the same thing. Okay, let's see. Dn, of course, is another important one. Dn, again, thinking about this shape up here, right? You know, we have all the, let's say this is a regular 6-sided polygon. We have the rotations, and then we have, you know, flips like that. And let's see, is there another kind of flip? I guess in this case, all the flips go through 2 vertices like that, right? And an important thing about this one, so this will be a flip, we'll have a rotation R, we'll have a flip. I think your book calls it S, I'll call it F. And the important thing about the DNs is that they're basically given by these relations. So you have Rn equals E, you can rotate around, you know, you have R, R1, R2, R3, right, up to Rn minus 1, and then you get back to E, right? You get back to where you started from. And if I do a flip twice, then I get E. And that's true for any kind of flip. And you know, this thing kind of has a front and a back, and anything that turns it over is a flip of some sort, right? So if I take anything like RKF or FRK, right, this will flip it over. I mean, the rotations don't flip it over, but it will flip it over. So this will be some other flip, right? And so in particular, any of these things, if I do it twice, will get me back to just E again, right? So one example of that would be RF. That's a flip of some sort. It's not this one, but it's a different one. But RF, because I've done it twice, will give me E, right? And actually, everything about the group is determined by those 3 relations, right? So everything else about the group is determined by those relations. You know, so for example, you have here that we can show that RKF is actually equal to F Rn minus K in this case, right? So that's a useful thing to remember about these. There's a whole bunch more about this in the visual group theory class, but I kind of like just reducing it down to these 3 simple relations and doing almost all the calculations based on that. Let's see. Oh, and the only other thing I wanted to do here was briefly look at this Group Explorer. It's kind of useful. So if we launch this like little web app, right, we can say, look at DN. So here's D4, for example. And you can, let's see, if I just click on that, I get all these different ways of looking at it. I can see its Cayley diagram. So, oops, let's see, oops, I didn't want the whole definition. I just wanted its Cayley diagram. All right, and so this is kind of nice because I can read this thing off. Now, in this case, he does his functions compositions right to left. We do our function compositions here in the usual way, left to right, but you can set this. I'm trying to remember how to set this. Oh, here, right? You can do left multiplication like that. So we get a slightly different Cayley diagram like this. And you can read things off. Like if I do R, F, right? So R then F, then whereas it's going to put me in here. And if I do R again, I get back to F, right? So this will show me that R, F, R will get me back to F, right? So you can use this to compute things. And let's see, and you also get you get a lot of information on these. Let's see, so you can see the subsets. These are all the subgroups that it's generated. So this is just a useful website. There's this thing called a CycleGraph. Here's the whole Cayley table, which is something that you had to do for one of your homeworks. Let's see if it loads. I'm not sure why it's taking so long. Let's see, let me just try loading it again. Let's go back here. Cayley table. There we go. Right. So usually loads pretty fast. Now here you can't change the order of multiplication, I think. And so here we're using the fact that he uses left to right multiplication. So you have to be a little bit careful about this. So this might look different than your Cayley table because we're using right to left multiplication. We're using right to left because these are actually functions, right? This is a rotation. It's doing something to some objects, right? It's rotating it. And then so the way we would read this is do R first, then F, right? But the way this is being read in the visual group theory is do F first, then R, right? So you have to be a little bit careful about that. So that's just something to remember. But this is a really useful site. If you want to know, and so this might come up. This will definitely come up in some of your exams and stuff. If I want to know like all the subgroups of D5, right, I can come here and just click on one of these things and look at the subsets. And the subsets will tell me all the different subgroups. It'll even tell me the orders, right? And so this will be really helpful at various points in the class. So this is a good tool to get used to using. And I've given you links. You have a link to the tool right here. And that's all I'm going to do.